All right, guys, let's get going today with the new learning unit. I think the last time I gave you guys an ice task to do in class. I think I gave you the whole session to finish that. Okay, all right, so we'll check that next week, Monday. Okay, anyway, for now, we're starting learning unit 3, which is probably going to be a bit of new stuff for you guys. So here we're going to start. Let's just look at the main sections. We're going to look at mathematical logic, theme 1. Theme 2 is sets and Venn diagrams. You guys might have dealt with a bit of this stuff in high school of theme 2. Theme 3 is sequences, but this is going to be a bit different from what you've done in high school. It's not just your traditional geometric, common first difference, common second difference. We go a little bit deeper. And then functions. Again, here, it's going to be a little bit more abstract. So this is where things start to get a little bit more difficult. So it's where I need you guys to try to pay attention. Everything else up until this point was not too bad. This is a little bit of memory work, unfortunately, in this section. So we're going to start with something called mathematical statements. And the examples we use start off as English sentences, which gets a bit strange, but it's a nice way to get into the idea of how these things work. Okay, so I'm going to start by defining the question. Maybe not. Did you check? It's not here. Okay, so maybe I should do that quickly so you guys can have the slides. And let me handle the tablet version of this so I can do that. Okay, sorry guys, let me upload that quickly for you guys. Now I can't see the top because of the screen sharing thing. Let me close something. Okay, so uploading for group 1. I think I updated the videos for you guys, so did anyone check? The videos should be all updated. Yeah. Okay, perfect. Okay, group 1. Slides. Okay, yeah, there we go. It's not here. Let's take that. Okay, so that should be there now for you guys to see. Oh, you 3. Okay, sorry guys, back to where we were. So we're actually getting through the stuff in relatively good time. It's already learning unit 3 out of 5. Yeah, guys, when you come in, please close the door. If anyone still coming in, come in. Okay. Sorry guys, we're recording here. If you're coming in, please come in. Or make the whole class wait, up to you. Statements. Mathematical statements. So a statement in mathematics is anything that declares something. If you declare something, you're making a statement. Like if I say, for example, the sky is blue, I'm making a statement. If I say, this example here, the moon is made of cheese, I'm making a statement. Even though it's not a correct statement, it's a statement. Right, so examples here of what statements are and what they are not. So everything up on the top here is a statement. 42 is a perfect square. Think anything where you're declaring something. And at the bottom are examples of things that are not statements. Obviously, a question is not a statement. Would you like some cheese is not a statement. The sum of two squares is not a statement. It's just like an incomplete sentence, not saying anything. Go to your room, not a statement. It's a kind of like giving someone an instruction, right? So command, yes, command is the word. Thank you. Okay, so statement is something that you declare, and statements have two types. These are atomic and molecular. Now, these are words we have to remember. And luckily, the words help us in the way they structure to remember what they are. Atomic is something fundamental. You can't break it down further. Molecular is something made up of more than one statement. So an atomic statement is just a single statement, like the sky is blue, the grass is green, whatever, things like this, right? A molecular statement is made up of atomic statements. For example, the sky is blue and the grass is green. That's molecular. I put two together, separated by an and. Okay, that's the basic idea. Atomic, molecular. Now we're going to look at these things called logical connectives, which are used to combine statements together. So for most of these, we use them to turn two atomic statements into one molecular statement. And these are typically what you imagine they would be. These are and, or, if, then, if and only if, not. The last one is a bit of an exception, but I'll explain that in a moment. Okay, so let me make some notes here. So firstly, we use something called propositional variables is the word to denote statements. Like when we're looking at just normal maths, algebra, we look at usually X, Y, Z as variable labels. Here we look at P, Q, R, S, capital letters, just convention, right? It's the same idea, just a letter to label a statement. So that's why we see all over here P's and Q's. Those are just labels for statements. Okay. All right, so now we need to get comfortable with reading things like this. Let me zoom in a little bit. So this right here is what you need to be able to read. This means the statement P and Q combined with an and, right? It's this little symbol, it's like an upward triangle. That's an and between two statements. And P and Q could be any statements. For example, again, the sky is blue could be P, Q could be the grass is green, anything like that. If you guys need me to slow down at any point, just let me know. Okay, and these emphasized words on the right here are the words we have to remember to tell us which logical connective we are dealing with. So the first one is and if you see the word conjunction, we know we're dealing with an and. Conjunction and this and upward triangle thing, they go hand in hand. They talk about the same thing. So let me just make P and Q be something so we don't have only abstract things to think about. P is sky is blue. Q is the grass is green. In the other group, I asked people for examples of statements, but I'm not doing that here because it went horribly wrong. Yeah. Some people said the earth is flat, and I was going to write it, but my hand wouldn't let me write it. Okay, so using these examples, we know what and is. That's the first one, a conjunction, the one I just circled. The one just underneath that, which is a downward sort of triangle, is an or statement. An or logical connective. So that would be stated as the sky is blue or the grass is green. So far, straightforward stuff, right? Just things to remember, really. Okay, and this one is called a disjunction. So an or logical connective, or rather, two statements combined with an or logical connective gives us the disjunction. That's the word. Okay, now the one underneath that is an if-then. Okay, so does anyone want to try to read our two example statements with an if-then? It doesn't have to make sense. Yeah. Exactly. Exactly. Right. So you guys are getting it. I'm hearing the right thing from most people. If the sky is blue, then the grass is green. Right. Again, doesn't make sense, but that's what the thing reads. And you guys will see as we go along, we're going to see a lot of things that don't make sense in English. But the whole point of this is to get us to a place where we can kind of understand logic gates. Okay, so the one underneath that is an if and only if. This one gets a bit confusing to say in English, but let's see if we can get it. This one here is a double-sided arrow. Biconditional is the word. Actually, let me go back one step. The one before this is called an implication or a conditional, but the word implication is very important because this one is so common. The next section deals only with implications. So we're going to deal with this separately in a moment. So this one is a special case. So remember the word implication. Okay. And the biconditional. Anyone wants to try to say that one with the statements we have? Yeah, that's it. That's it. Yeah. Okay, so most of you guys are getting it. Maybe it's not as bad as I thought it was. Okay. The sky is blue if and only if the grass is green. I'd literally just read it as it's written here. Okay. Yesterday there was some confusion going along with things like if and only if the sky is blue, then the grass is green. It was just getting messed up. And then I started getting confused because, but anyway, it's not as bad. So it's okay. Okay, and the last one is a special kind of logical connective because it doesn't connect anything. It just applies to a single statement. That one is called a negation. It just undoes a statement, so it's not. So whatever the statement is, this tells you the opposite of it. Okay. Okay, and let me also note that the first four connectives are called binary because they connect two statements, and the last one is called unary. Okay, guys, this is all new stuff. So do we have any questions before I move on? Okay, we'll dealt with that. So now we're going to think about something called truth values. Okay, so this is important because this is where the bulk of the section comes in. Truth values of statements is, well, first simply put, whether a statement is true or false. Now that's usually given to you. You're given a statement and usually you're told whether it's true or false. But the tricky thing is to then determine whether the molecular statement, which is made up of atomic statements, based on the truth value of these atomic statements, what can we say about the truth value of the molecular statement? So that's what we look at now. And we have a set of rules for that. Examples of statements, I'm going to skip that because we had disasters last time. Truth value. So this is the table that we need to commit to memory. Okay. So maybe some examples will be helpful here, but let's just see what the table is telling us. So the truth condition. So what the first line here is saying, the first point is saying that two statements combined with an and. What is the word for that? Was it conjunction? Conjunction, right? So a conjunction is true when P and Q are both true. So that's what we need to know based on the individual atomic statements, truth values. What can we then say about the combined molecular statement's truth value. Close conjunction. This junction at the bottom here is true when P or Q are true. So as long as one of them is true, then the entire thing is true. Right? And I think we're going to have to make up some examples just now because it's getting a bit abstract, isn't it? Okay. Yeah, we can do that. I'll let you guys make up for this one and let's see how it goes. Okay, so the implication becomes a bit tricky. This is where people start making mistakes here. This is true when P is false or Q is true or both, but that or both doesn't make a difference. It doesn't really change anything. So we can essentially ignore that or both part. It doesn't really change anything. Let's say when P is false or Q is true. Both is kind of saying that if there was an and here, it wouldn't make a difference. But again, if that's confusing you, forget about it. That or both essentially adds no value to this thing. It's of no consequence. Okay, and again, instead of continuously reading these things, let's just make up some examples. I need to make up examples where the truth value is not obvious. Like if you say the earth is flat, for example, we can immediately say false. So let's make up something which is not obvious. I'm going to write it here. Okay, so let's say, I'm just going to say P is, let's see, something that's not obvious. Okay. Thank you. But I'm going to have to impose a value on this later. So let me use something else, because if I say true and false, people are going to go home and tell their parents that Shamik lied to them. So let me write here. I'll use my name so no one can say anything. Shamik got 39% for maths. Okay. Q, I'll say just using my name because I don't want anyone to complain. Shamik owns a true or false, you can decide, right? Okay, so these are things. Maybe at some point we can hope. Okay. Yeah. So I'm going to phrase this in the form of a question. The type of question you guys will get will be, let's say, okay, example. Say suppose, okay. Suppose P is true and Q is false. Then what is value of one is P and Q, two is P or Q, if P then Q. Okay, so guys, with a question like this, it's probably not helpful if I just immediately blurt out the answers. So what I'm going to give you guys a moment to do is to look at this table. Let me open it up again. If you need to take a picture or screenshot or whatever of this, do that because you're going to need it for the example. And then use this table to try to work out the example for yourself. Okay, when you guys all have it, let me know, then I'll switch back to a question. Okay, I'll give you a moment. Now, I want you guys to really apply yourselves and think about this. Try and work it out. Think about what they're asking and how to work it out. I sent it around already. And it came back so quickly. Okay, guys, here T is true and F is false, in case it wasn't clear. Yes, just true or false. Yeah. Yes, register. Any of you guys did something like this in high school? That is. Sorry, my handwriting is a bit. Okay, guys, anyone needs more time? Okay, so let's do it. The first one, let me try and make more space here so I can write this in a certain way. Okay. So again, you guys will notice that the original statements that I wrote at the top, it doesn't matter. It makes no difference for this. All we need to know is the truth value, which is given here at the bottom. We know that P is true and Q is false. So knowing that, let me write in a different color here. P is true and Q is false. Is that enough for this entire thing to be true? It's not, right? So this one is false. Okay, so I made too much of space. The one at the bottom, same story. P is true, Q is false. What does that tell us about the combined thing? It's true, right? Because we just need one of them to be true. Okay. So now this is where things get a little bit tricky with this implication. Let me just make space for this one. Okay, so what we know is that is true and that is false. Let me write on the side here. The condition we need is we need P to be false or Q to be true. This is an or. The or both doesn't matter. So forget about that part. So is P false here? No, we didn't meet that. Is Q true? None of them are met, so this one is false. Yes. Yes.
Would that be true?
Yes. That would not depend on the. I mean, sorry, you mean if P was false?
Yeah, if P were false
Yeah.
or if Q. Like,
Yeah.
so is
I get you.
Like, yeah, I understand. Q was false.
Yeah. Q is
this
false.
is true.
Q is false.
Oh, okay.
Q is true.
Yeah.
Must be true.
Yes.
So at least one of them has to meet.
Yeah. So because this is an or in this condition, as long as one of them is met, then the thing is true. If none of them are met, it's false. Okay. Yeah. Yeah. So don't worry, guys. Straight after this, I designed an example with only the implication where we look at all the possible cases. So that will be helpful. Okay, so anyway, let's look at the next one, for which I'm not sure if I remember the rule. I think this one says both need to be true or both need to be false. All right, so this one here, one is true, one is false. So that's immediately false, right? Okay, and the negations are easy. We know that P is true, so that means the opposite of P. The negation of P is then just the opposite truth value, false, right? And the same with Q. We're given that Q is false, so not Q is then true. Just the opposite. Okay. Is someone talking to me in the back? Okay. Okay, so far I think everyone's okay with most of this, with a bit of confusion about the implication. That's okay. We will get to that in a good amount of detail. Probably now, I think. Okay, sorry, are you guys still writing this down? Anyone's writing? I'll leave this on the board. Okay, don't worry, I'm not rushing you. Okay. I'm just using the whiteboard so that it's on the video when I upload it. Yeah. Okay, now why am I doing that? That's what I'm doing. Okay. Okay, so we look at, this is the example for an implication, but before we do this, there's something here to be said. Yeah, they're saying what we kind of know. Implications are so common that they deserve their own subsection, which we're going to look at coming up now. And there's a quick example here to say that, just for example, the way we usually speak about things, like the theorem of Pythagoras, for example, is technically supposed to be an implication, but we don't usually state it that way, right? But the proper way to say it would be as an implication, right? You guys know Pythagoras says that a squared plus b squared is c squared. You guys know that rule with a triangle? Okay. So now, if I just say that, I'm not defining A, B, or C, I'm being a bit ambiguous. So the correct way to say that is the way it says right up here. If A and B are the legs of a right triangle with hypotenuse C, then A squared plus B squared is C squared. So we've got to quantify the A, B, and C, where they come from, what they represent, and then we can give the formula. So it's a if something is true, then Pythagoras, right? So implication. Okay, so having said that, let's see. Okay, it's now 10:40. You guys can start the example and finish it after the break if we don't finish it now. So let me try and make this whole thing visible on the screen. So again, the same thing, just find the truth values of each of these from 1 to 8. Are they true? Are they false? That's what we need to know. Yeah. Okay, so that's a good one. So the first thing is we just need to find the statements. So the first statement is, we can see clearly it's an if then, right? So the first, after the if, it says Bob gets 90 on the final. So that's P, we'll call that P. Then Q is the one after the then. And then each question, each one, 1 to 8 is just telling us something about whether he did get 90, whether he didn't get 90, whether each P or Q is true or false. And then from there, we use the table to determine. Did I confuse you more?
Okay. Where do you like it? Yes. That's what I'm not saying it was, but you know, you have a screen of.
Implication instead of whether that is okay. Okay, guys, I think we're having a bit of trouble here, so let me do the first one for you guys. Okay, guys, I'm going to do the first one. All right. Okay, so for the first one, what we need to do is, first, let's identify what kind of statement are we dealing with here. This is the statement, right? It's clearly an implication, right? So because it's an implication, we need to identify P and Q here. So let's identify the statements. Bob gets a 90 on the final. That goes up to here. So we'll call that P. That's the first statement. The second one is Bob will pass. Bob will pass the class. We'll call that Q. That's the first thing. Identify your statements and check what kind of molecular statement we have here. So this is clear here. If P, then Q, right? Yeah, so that's what the thing is. So now the question is asking us essentially to determine under which circumstances this statement, this molecular statement, is true or false. Right? That's what we need to determine. I know it works in a weird way. Under which circumstances the statement is untrue. That's basically asking you when is it true or false. Right? And then you can say whether it's untrue or not in these weird words. But all we need to know is whether it's true or false. That's the main thing here. So once we have this, we know that the truth value for an implication is given by P needs to be false, right, like this, or Q needs to be true. And each number here tells us something about whether P is false or Q is true, or both, or neither. So let's do 1, for example. 1 is basically telling us Bob gets a 90 on the final. So this is telling us that P is true, right? So based on P being true, let's look at the implication again. I'll rewrite it here, where we know P is true and know nothing about Q. We know nothing about Q, but we know P is true. So what can we then say about the statement based on the rule, which we need to remember, which is up here? Let me think for a second. So we need P to be false for this thing to be true. That's not true. So we need Q to be true. Is that met? Okay, this false. P needs to be false according to the rule of object.
But it's always going to be true. No.
Okay, let me take it back a second. Okay. Do you guys want to try again after the break? Okay, take your break.
I think I've lost the point. What exactly we're trying. We're trying to make a P.
Which one? P. This is telling us P is true.
Yeah.
Yeah.
Is it false or true?
We're trying to determine whether this thing is true or false in each case.
Okay, so the statement, consider the statement is saying whether P arrow is true or false.
Yes, exactly.
Yeah, no,
Exactly. Yeah.
So we're saying true or false?
We're just saying true or false. Okay, I'm stopping the video here. I'll restart again just now.